Hello viewers, in today's lecture we are going to study about linear differential equations. Let us first take the definition of linear differential equation. A differential equation of the form dy by dx plus py equal to q, where p and q are constants or functions of x only, is known as a first order linear differential equation. So viewers, suppose we have an equation say dy by dx plus xy is equal to say sin x. Now this is a linear differential equation of first order. If we compare these two equations, we see that p is equal to x and q is equal to sin x. And in the definition, we have said that p and q are constants or functions of x only. So here p is equal to x and q is equal to sin x. So p and q are functions of x only. Clear? Okay. Let us take one more example. Suppose we have a differential equation of this type. Say dy by dx plus y is equal to say cos x. Now here we see that if we compare these two equations, this with this, we have p is equal to 1. Clear? Here we have 1y and q as cos x. Now here p is a constant. P is a constant and cos x is a function of x only. Clear? So a differential equation of the form dy over dx plus py is equal to q, where p and q are constants or functions of x only, is known as a first order linear differential equation. Clear? Now let us take one more example. Suppose we have an equation of this form, say x dy by dx plus 2y is equal to x square. Now here this equation it doesn't look like this equation, but if we divide both sides of this equation by x, we have dy over dx plus 2 over x y is equal to x. Clear? We divide both sides by this factor x. Now we see that this equation is now comparable with this equation, and p is equal to 2 by x and q is equal to x, and p and q are both functions of x only. Clear? Now viewers, let us find the method to solve this first order linear differential equation. Clear? Now viewers, here we have the equation dy over dx plus py is equal to q, and we want to solve this differential equation. Now let us multiply both sides by a function say f of x. Clear? So therefore we get f of x dy over dx plus py f of x is equal to q times f of x. Say this is equation number 2. Clear? So we have this equation and we want to solve it. Let us multiply both sides of this equation by a function f of x. Clear? Now viewers, here we have the right hand side q of fx. Clear? So this is the right hand side and this is the left hand side. Now if we want to express this fx in such a manner that this right hand side becomes a derivative of y times f of x. Clear? Okay, so let us consider the derivative of y times f of x. Clear? So what we will get? We'll get this is the product of two functions. So we'll use here the product rule. So y times the derivative of f of x, then f of x derivative of dy over dx. Clear? Okay, now here the value of fx times dy over dx can be written as fx times dy over dx can be written as d over dx y times f of x minus y times d over dx of f of x. Clear? Okay, so viewers, let us substitute this value fx times dy over dx in equation 2. So what we will get, we'll have d over dx y times f of x minus y times d over dx of f of x plus p times y of fx is equal to q times f of x. Clear? And now this can be written as d by dx of y fx, and we have minus y. The derivative of f can be written as f prime of x plus py f of x equal to q times of f of x. Clear? Now viewers, here in equation 2 we have said that we are choosing this function fx in such a manner that the right hand side, this right hand side becomes the derivative of y times of fx. Clear? So therefore we must have p times y f of x is equal to y f prime of x. Clear? So this can be written as p f of x is equal to f prime of x. Clear? We can write it like this: p is equal to f prime of x divided by fx. Clear? Now if we integrate both sides with respect to x, we have integral of p, and here we have f prime of x divided by f of x and dx. Clear? Now this can be written as I am writing it here. We have integral of p is equal to this is a log of f of x. Clear? And by using the definition of exponential function, we can write f of x as e raised to integral of p. Clear? So where's the function which we have selected, and we have multiplied equation 1 by f of x is ultimately equal to e raised to the integral of p. Clear? and this function f of x is known as the integrating factor of this linear differential equation 1. Clear? So this is the integrating factor of the linear differential equation of first order, and this is denoted by IF. Clear? So the integrating factor is equal to e raised to integral of p. Clear? Okay. Now the next step is to find the solution of this differential equation. Clear? Now we multiply equation 1 with this integrating factor. Clear? Which is e raised to integral of p. So let us multiply equation 1 by this factor. So we have e raised to p dx, integral of p, we have dy over dx plus py, and then integral of p dx here equal to q times e raised to integral of p. Clear? Now viewers, let us look at this expression. Now this expression can be written as the derivative of, we can write it as the derivative of y multiplied e raised to integral of p. Clear? And here we have q times integral e raised to integral of p. Clear? So here this expression is expressed like this because if we take this as the first function and this is as second function, and if we apply the rule of derivative of product of two functions, we'll get this expression. And the rule is if we have two functions of x as u and v, then the derivative of the product of u and v is given by u times derivative of v, and then we have v derivative of u. Clear? So we have first function as say y, we have y, then derivative of this integral e raised to p dx we have, and then by chain rule, if we differentiate this, we have p. Clear? Then we have the second function as e raised to integral of p, and then the derivative of y. Clear? Or in other words, we can say that u is y here and v is e raised to pd integral of p dx, and the derivative of v with respect to x is e raised to integral of p, and then by chain rule we have p. Clear? So from this equation, say this equation is third equation, now we integrate both sides. Clear? Now we will integrate both sides with respect to x. So integrating both sides, we have d over dx, and here we have y times e raised to integral of p, and here we have dx. We are integrating both sides, then we have here q times e raised to integral of p dx, and here we have dx and plus c as the constant of integration. Clear? Now viewers, now we can write this expression as the integral of d by dx of y times e raised to integral of p as y times e raised to integral of p is equal to integral of q times e raised to integral of p with respect to x and plus c. So this is the solution of this linear differential equation, and if we denote um, e raised to integral of p with respect to x as if, then this expression can be written as y times the integrating factor is equal to integral of q, here we'll have dx also, and q times integrating factor dx plus c. Clear? So this is the another form of this solution. Clear? Okay. Now viewers, let us take one simple example to illustrate this method. Now viewers, suppose we have to solve this differential equation. Now when we take a close look at this equation, we find that this equation is similar to this equation. So we declare that this equation is of the form dy over dx plus py is equal to q. If we compare both these equations, we see that p is 3 and q is e raised to minus 2x. Clear? Now the integrating factor of this differential equation is e raised to integral of p with respect to x. Now we have integral of p means 3 we have, and here we have dx, and this is e raised to 3x. Clear? Now the integrating factor of this differential equation is e raised to 3x. Now the solution of this differential equation is given by this expression. So we have y times integrating factor means e raised to 3x. Here we have integral, the value of q is e raised to minus 2x multiplied e raised to 3x dx plus c. Clear? Now we can write it as y times e raised to 3x equal to this is e raised to 3x minus 2x is x dx plus c, and we can write it like this: e raised to 3x is equal to e raised to x plus c. Clear? Now this can further be written as, I am writing it here, we can write it as y is equal to dividing both sides by e raised to 3x, we have e raised to minus 2x and plus c times e raised to minus 3x. Clear? So this is the general solution of this differential equation. Clear? And now viewers, here we have the linear differential equation of this form, but in some cases we may have a linear differential equation of this type also: dx over dy plus px is equal to q. Clear? So here we have dy over dx, here we have dx over dy, and here we have py, here we have px, and here we have q. In equation 1, in this equation we defined p and q as constants or functions of x only. Clear? But in this equation of this type, linear differential equation of this type, we define p and q as constants or functions of y only. Clear? Functions of y only. Clear? And the method of solving this type of linear differential equation is absolutely same as we have done in equation 1, with the difference that in equation 2, the integrating factor will be e raised to integral of say p and dy. Here the variable is y, and here we have dx. Here we will have dy. Clear? And the solution of this equation 2 is given by, here we have y, so we have x here, x times the integrating factor is equal to q times integrating factor, and here we have dy plus c. Clear? So when we have linear differential equation of this type, that is dx over dy plus px equal to q, where p and q are constants or functions of y only, then the integrating factor will be given by e raised to integral of p with respect to y, and the solution of this differential equation is x times integrating factor is equal to integral of q times integrating factor with respect to y and plus c. C is the constant of integration. Clear? Now viewers, here I would like to mention one more thing, that we have to remember here one important property of exponential function, and which is e raised to log of f of x is equal to f of x. Clear? So always remember this property, because we are going to use it while solving problems based on these two types of linear differential equations. Here, for example, if we have an expression like e raised to log of x, then it is equal to x. Similarly, if we have e raised to log of say x square plus 1, we have x square plus 1. Clear? So keep this important property in your mind while solving problems based on equation 1 and equation 2. Clear? Now viewers, let us take this problem. Now here we have to solve this equation, and let us divide both sides by x. Clear? So we have dy over dx plus y over x is equal to x square. Clear? Now this equation is same as this equation. Clear? Dy over dx plus py is equal to q, and therefore here we claim that this is a linear differential equation of first order of this type, and p is equal to 1 over x and q is equal to x square. And here we see that p and q are functions of x only. Clear? Now the integrating factor will be given by e raised to integral of p with respect to x. We have integral p is 1 over x, and dx we have here we can write it as e raised to log x, because integral of 1 over x is log x, and I have just told you the property e raised to log of fx is equal to f of x, so this is equal to x. Clear? The property is e raised to log of f of x is equal to f of x. Clear? So here's the solution of this linear differential equation is y times integrating factor integral of q times integrating factor, we have dx plus c. Now we substitute the values. Integrating factor is x, and here we have q as x square, and here we have the integrating factor as x, and here we have yx, and this is x cube dx plus c, and this can be written as x raised to 4 over 4. The integral of x cube is x raised to 4 divided by 4 plus c. Clear? Now dividing both sides by x, we have y is equal to x cube over 4 plus c over x. Clear? So this is the general solution of this differential equation. Clear? Now we are here, suppose we were given the initial conditions as say x is equal to 1 and y is equal to 0, then we can find out the particular solution of this differential equation. If we have to find the general solution, then it is sufficient to find y is equal to x cube over 4 plus c divided by x. But if we have these conditions also, then we can find the value of c. So let us find and substitute these values. So y is 0 here, and we have x cube, that is 1 cube over 4 plus c over 1. Clear? Now this is equal to 0, 1 over 4 plus c, so c is equal to minus 1 over 4. Now if we substitute this value of c in the general solution, we get the particular solution as y is equal to x cube over 4 and minus 1 over 4x. Clear? Now viewers, let us solve this problem. Now this problem we have to first convert this differential equation into a known form, and if we write it as y dx is equal to x plus 2y square dy, it means we are simplifying it, and we can write it as dx over dy is equal to x plus 2y square over y, which can be written as x over y plus 2y, and this can further be written as dx over dy plus we have minus 1 over y, x is equal to 2y. Now viewers, here we see that this equation resembles with the linear differential equation of first order of this form, dx over dy plus px is equal to q. And here if we compare both these equations, we have p is minus 1 over y and q is equal to 2y. Clear? Now the integrating factor of such a differential equation is given by e raised to p dy. Clear? Now we can write it as minus integral of minus 1 over y with respect to y. This can be written as e raised to minus of log y. This can be written as log of 1 over y, which is equal to 1 over y. Now the solution of this differential equation is given by x times integrating factor is equal to integral of q times integrating factor. We have dy plus c. Clear? Now substitute these values here. We have x times integrating factor is 1 over y. We have q as 2y times 1 over y dy plus c. Clear? Now this is x over y, y get cancelled. Here we have 2 integral of dy plus c. This can be written as x over y. This is 2y plus c, and this can be written as 2y x equal to 2y square plus cy. Clear? So this is the general solution of this differential equation. Clear? Now viewers, let us solve this differential equation. Now this differential equation can be written after dividing both sides by 1 plus x square. So we have dy over dx plus 2x divided by 1 plus x square. Here we have y, and here we have 1 over 1 plus x square whole square. Clear? Now viewers, this equation is of this type. Clear? So we have dy over dx plus py is equal to q. So this is a linear differential equation of first order of this type, and where p is 2x over 1 plus x square, and q is 1 over 1 plus x square whole square. The integrating factor of such differential equation is given by e raised to integral of p with respect to x. So we have integral e raised to integral of p is 2x divided by 1 plus x square dx. Now here we see that this is a simple integral. The derivative of 1 plus x square is 2x, so this is directly e raised to log of 1 plus x square. Now the property of exponential function, this is equal to, because e raised to log of fx is equal to fx, so this is 1 plus x square. Clear? So here we have used e raised to log of f is equal to f. Okay, now the solution of this differential equation is given by y times integrating factor is equal to integral of q times integrating factor. We have dx plus c. Clear? Now let us substitute the values. So we have y times integrating factor is equal to 1 plus x square. This is the integrating factor, equal to integral q is 1 over 1 plus x square times the integrating factor 1 plus x square dx plus c. Clear? This can be written as y times 1 plus x square is equal to, here this term get cancelled with power here 1, it becomes 1. So we have integral dx over 1 plus x square plus c. Okay. Now viewers, here this is y times 1 plus x square is equal to integral of 1 over 1 plus x square is tan inverse of x plus c. Clear? So this can be written as y is equal to tan inverse x over 1 plus x square plus c over 1 plus x square. So this is the general solution of this differential equation. Clear? Now if we want to find the value of c, we will make use of these values. So y is equal to 0 when x is 1. So we have 0 equal to tan inverse 1 over 1 plus 1 square plus c over 1 plus 1 square. Clear? Now this can be written as, here if we solve it, we have 0 is equal to tan inverse of 1 is pi by 4, and we have 2 plus c over 2. Clear? So here we have 0 is equal to pi over 8 plus c over 2, and c by 2 is equal to minus pi by 8, and c is equal to minus pi by 4. Clear? Now we substitute this value of c here. So the particular solution of this differential equation becomes y is equal to tan inverse of x divided by 1 plus x square plus minus pi by 4 divided by 1 plus x square. Clear? So this is the particular solution of this differential equation. Clear? Now viewers, let us solve this problem. Here we have cos square x dy over dx plus y is equal to tan x. So let us convert this equation in this form. So dividing both sides by cos square x, we have dy over dx plus y over cos square x is equal to tan x over cos square x. Clear? Now this can be written as dy over dx plus sec square x y is equal to tan x sec square x. Clear? Now this equation is of the form dy over dx plus py is equal to q, and this is p and this is q. Clear? So p is sec square x, q is tan x sec square x. Clear? So the integrating factor is e raised to integral of p with respect to x. So we have integral of p is sec square x dx. So we have e raised to the integral of sec square x is tan x. Clear? So this is the integrating factor of this differential equation. Now the solution is given by y times integrating factor is equal to integral of q times integrating factor, we have dx plus c. Now substituting the values, so we have y times e raised to tan x, and we have integral, the value of q is tan x sec square x times the integrating factor is e raised to tan x dx plus c. Clear? Now here our aim is to evaluate this integral. Clear? Now for evaluating this integral, we will make use of substitution method. So let us put t is equal to say tan x, then we have dt is equal to sec square x dx. So therefore this equation becomes y times, here I am not substituting t for, or we can say let this integral be I. Clear? And the integral is tan x sec square x e raised to tan x dx. Clear? And we make the substitution. So we have for tan x we have t, sec square dx we have dt, and here we have e raised to t and dt. Now by making use of integration by parts, we can solve this integral. This is the first function, e raised to t is the second function, then we have the derivative of t here integral of e raised to t dt and dt. Now this is t e raised to t minus the derivative of t is 1, integral of e raised to t is e raised to t dt. We have t e raised to t minus e raised to t, and this can be written as e raised to t minus 1. Clear? Now if we substitute the value of t as tan x, we have e raised to tan x, and we have tan x minus 1. Clear? Now therefore the value of this integral is this. Clear? So substituting this value here, we have the final solution as y times e raised to tan x is equal to, we have e raised to tan x, we have tan x minus 1 plus c. Now this can be further written as, if we divide both sides by e raised to tan x, so this get cancelled here, we have tan x minus 1 plus c times e raised to minus of tan x. Clear? So here's, this is the general solution of this differential equation. Clear? So here's in this lecture we have solved some problems related to linear differential equations. Thank you.